So we're going to learn about logical connectives, among other things, but logical connectives, the ways of combining two thoughts together and to try to make a logical conclusion from it. So I'm going to start off with the basic connectives, which is the and the or, and then we'll get into the implication. All right, so the and is denoted by kind of, like I call it an almost A. All right, so you have that upside down V, that stands for and. It's a conjunction. Well, we think of it in lay terms, add, no, and. And the disjunction is denoted with an ordinary V, but our lay term for that would be the word or. All right. And then we have the implication, which is the if-then, which is probably the more complicated. Well, definitely the more complicated. All right, so the sideways arrow, minus the little apostrophes there, those are just to accentuate. I don't even know why I have them there. But the conjunction, it's when you put two statements together with a conjunction with an and, the only way that sentence would be true is if both parts of it were true. All right, so I always have simplistic examples, and I mean that in every sense of the term. I am wearing shoes and I am wearing socks. All right. Now we can verify the truth of that sentence by seeing if I'm wearing shoes and socks. I'm not going to prove it, but like if I'm missing either one of those two things, then I'm not telling the truth. All right. The statement would be false. All right. So if I'm up here with sneakers on with no socks, it's a little cold out for that, but that would not be a true sentence if I'm telling you that I'm wearing shoes and socks. Now, if I'm telling you that I'm wearing shoes or socks, now it could be that I'm just wearing socks. It could be that I'm just wearing shoes, but it also allows for me to be wearing both. Now, the tricky thing about an or is it makes it feel like it's a choice. Like if I say I am wearing shoes or socks, well, if I'm wearing both, it feels like I'm like violating the rules, right? The word either would be an important component there. If I say I'm wearing either depending on how you pronounce it, either shoes or socks, now I'm making it into a choice with that qualifier of either. All right, we're not working with that here. Here it's just a simple or, and I like to call it the mathematical or, which because it kind of puts it into a different category where you say, okay, well this is just true because it's the math or, but if I say that I'm wearing shoes or socks, it does allow for me to be wearing both shoes and socks. All right. So that automatically it's a little mind bendy, but logically, and the trick about logic is that we come up with rules that allow us to draw conclusions, and they could be wrong. We call it propositional logic. These rules could be incorrect. It's just that's what everybody else does. So like on another planet, they may define or as being a choice, right? But we define it this way because the people who came before us defined it that way, right? Now, if you make one small change in the way you look at things, like the definition of and the definition of or, there would be a cascading effect all the way through logic that would change most, I would say, of all of the rules that we know to be true. All right. The if-then is a little bit more complicated. Well, I'd say a lot more complicated. It's not complicated in the way that we use it. It's kind of complicated in the way that we think of it. All right. And you could tell by the blurb that's written there. The statement P then Q. So when I look at a statement P with a sideways arrow, I'm reading this as if P, then Q. All right, so that's what this is telling me. This expression here is saying, it's translated to if P, then Q. All right. What that's saying is that there's some premise, P for premise if you want, some premise that would lead to a conclusion. All right. The P is the premise, the Q is the conclusion. All right. So an example would be, if I earn a 90 or above in this class, then I will get an A. All right, I'll make a little note of that. I'll just jot that down. If I earn, but it's also a true sentence related to this class. If I earn 90 or above, I will get an A. I mean, I suppose I should throw the word then in there to be consistent with the way I've wrote it above. Right. It's just the thing is, when we speak in everyday language, we kind of omit certain words. You know, like going back to the either or. If I say I am wearing shoes or socks, it's interpreted as I am wearing either shoes or socks. Right? We leave off the word either, but people know what we're talking about anyway. Right? If I earn a 90 or above, I will get an A. There's an implied then in there. It doesn't have to be there in order to be implied. Right? Or you could read it the other way. I will get an A if I get a 90 or above. Right? Either way means the same thing. All right? But this is really more like a contract. When I use a conditional if then, I'm telling you what will happen if the premise is met. All right? The problem is I'm not telling you what will happen if the premise is not met. All right? So if it turned out, like I'm a student, I just got a 95 average at the end of a course, based off of this sentence, I would expect to get an A. That would be the case of true then true. And that would be equal to true. All right? And, you know, like notation aside, and I honestly, I believe that math only feels more complicated than it is because of the notation. And maybe not in this moment. Maybe it makes perfect sense right now. But like 2 weeks from now, when you go back and review these notes, you'll be like, what on earth? The T sideways arrow T equals T? Where did you get that? What does that mean? Right? That's one of the reasons why I record videos. But, you know, you don't always have to go online, look up class videos. You could also just ask. Hey, I was looking through the notes and I noticed that. What does that mean again? You know, that's perfectly fine. So, yeah, this means that I got the 90, 95, 99. Maybe I got a 200 somehow. A lot of bonus now. You'll never get that high. But then I was awarded an A. Right? If the first part of the sentence is true, false, and the second part is true, this is where it gets dicey. That's also going to return a true. And that doesn't feel right. It doesn't feel like that makes sense, but it does. Because I said so. No, because here's the explanation. I never told you what would happen if you didn't get 90 or above. All right? So let's say you got an 85. Did I break this contract if I still give you an A? And that's the thing. When we're looking at conditionals, if then, we're looking at as a fulfillment of a contract. Yes, the contract was fulfilled. True. No, it was not. False. So if I tell you what will happen if you get a 90 or above and you get an 85 and I still give you an A, maybe I'm just a nice guy, but I didn't break the rules. Right? Because I didn't have a rule in place if you got an 85. I only had it for 90 or above. Right? So there's that gray area, but that defaults to a true value. Same thing, false, then false. If you get an 85 and I don't give you an A, I didn't break the rules. I only told you what would happen if you got a 90 or above. If you get an 85 and I give you a C, that's not very nice of me, but I still didn't break this contract. All right. If you get an 85 and I give you a B plus, that's what I should give you, but still has nothing to do with this contract because we didn't satisfy the premise. All right. So this would be a true. right? Because even though the contract doesn't apply, I didn't break the contract. Right? Breaking the contract is the only way to get a false when it comes to a conditional. So that brings us to the last possible case. True, then false. You got a 95 and I gave you a B plus. Not only am I not a nice guy, but I also broke the contract. Breaking the contract gets me a false. All right. By the way, that'll never intentionally happen. All right. So if you get a 95, I'm not going to look for ways to bring you down to the B grade just because I've already given out too many A's. And like that's not how it works for me anyway. I know when I was in school, I can't speak to my contemporaries, but when I was in school, there were some classes where I'm only giving out 5 A's, and there's 30 people in the class, and now it's like a battle royale to find among the students to be the highest score earner in the class. That's I mean, if anybody still does that here, if I don't even know if anybody actually did it here ever, but if that happens here, that's not a good thing to do, right? I know in business schools, they like to foster competition in the classes, right? Because that's how it's going to be when they get out into the workforce. So it's competitive. So they throw that little element in there, right? 50 students, only 10 of you are getting A's, and oh, by the way, 10 of you are also going to get an F. I remember those stories. I never experienced it, thank the maker. But I do remember students being like, wait, so I could have a 90 average, but if I'm in the bottom of the class, I get an F? And the answer to that was, yeah, you do. Those could also be like urban legends or myths to dissuade people from going to business school. You thin down the competition by scaring away half the people that could come in. Yeah. So those are examples of connectives. There are others, specifically in if and only if, but that's not something that we're going to focus on for the foreseeable future. But what we want to be able to do is get an idea of what an and or an if then look like graphically. All right. And really, I mean, you'll find in a lot of areas of math, you make graphs for the sake of making graphs. It's like, here's an equation, solve it. Now, what else can we do? Graph it. Go ahead and graph it. That'll kill another 5 minutes. But there's value in learning that. It's not always presented that way. All right. Here, there's more than just a little bit of value associated with it. This is a fundamental to our understanding of probability. All right, being able to handle Venn diagrams and understand and interpret what they mean. All right, first off, I throw this notation at you here with that upside down U. All right, the upside down U is the set notation for and. All right, so it's basically the same idea as the upside down V. All right. So the same concept is what we wrote up in the top related to the logic of it. Same concept, slightly different notation, just a little curved. Right? And that's what I was saying before, where sometimes the notation gets in the way of understanding. Right? This is set notation for and. You can treat it as the same way you would treat the upside down V. Oops, I don't need the quotes. All right, so think of these two as equivalent. So why do we need the different form of notation if it means the same thing? 2 reasons. One, a little bit more practical. I just want you to be prepared that if you see either of these forms of notation in a textbook, online, whatever, in another class, you'll know what the heck it means. So that's one. The other is a little bit more, I'll keep it vague, but historical. it's really different areas of the world came up with the same concepts at different times, maybe at the same time, and everybody had their way of noting those concepts. All right, so whether it's simple operations, addition, subtraction, stuff like that, like we have the dot way of representing multiplication, and you have the X way. All right, different people get to the concepts on their own independently and create their own notation. So what we have to do many years later is kind of marry the two ideas, right, and know that they're equivalent to one another. It's almost like translating to a different language, but in a mathematical sense, right? So if I look at this Venn diagram, and again, Venn diagrams really just show the relationship between different sets of information. Right? It could be the number of people who like ice cream, the number of people who like hot chocolate. Yeah, there's going to be some overlap there. There's going to be people who like ice cream and hot chocolate. Right? So how do we represent that? So what we do is we look at set A as being its own circle, set B as being its own circle, and what this is talking about is the overlap between the sets. All right, so it's what's in common from one set to the other. Right? Context really drives that. It's not always easy to pick out like what the relevant variables are, but when you do, it's not too bad after that. I'm just going to do a quick demonstration, really, of how this works. It's not something that you're going to be able to write down, just because I'm going to kind of animate some things on the screen, but hopefully it'll get the point across. So I'm just going to draw on the side here another box. Let me get the shading out of there. I'm going to put a couple circles in. It's the thing about technology. It's a wonderful thing if everybody has access to the same sort of technology. Because I've had plenty of students over the years that are like, hey, you know how you write that stuff up on the board? That's really nifty. How can I do that? Well, get an iPad with an Apple Pencil and the app, which costs like $10, and you can do that. And it's like, oh, okay. You lost me at Apple Pencil. Like whatever. All this stuff involves money, So fortunately, I've been lucky enough to have schools that would provide me with this stuff to make at least the demonstration part of it a little easier. All right. I made my rectangle too big, so I'm gonna redo that. I mean, it really doesn't matter. It just doesn't look very nice. So, and let me get the shading out of there again. Okay, so I'm gonna duplicate this, copy, paste. All right, so I'm looking for the overlap of the sets of A and B. All right, so let me just kind of bring it in here. Here's my set A, and here, well, in both cases, set A, set B. All right, if I shade in everything in A, that would give me all the outcomes associated with whatever the event of A is. Okay, so maybe, like I said, these are the people who love ice cream. And the other group, B, would be all the people who love, what did I say, hot chocolate. All right? What I'm looking for is the vergence of these two sets. Like, if I pick one up and drag it on top of the other, which part would be shaded using both colors? Now, it's hard to see because foolishly I chose two colors that are kind of the same hue. Try this. Pops a little bit more. All right, that little green area in the middle, it looks a little bit greener than it did before. It's good. Yellow and blue should make green. The app isn't like perfect, but it is definitely some sort of shade of green. Although my color blindness might be an issue. I'm not fully colorblind, but like many of you probably experience the same thing where it's like you have trouble with the grays or the purple, stuff like that. My my wife and I were sitting down looking. I needed to buy a jacket because we're going to go up to Quebec in a month, and I wanted to get something that's pretty heavy duty. And she's like, "What about this jacket?" And I was like, "That's a nice jacket." Oh, they're out of. I wanted black. She's like, "They're out of black." And then she goes to the other color, and I was like, "Oh, that's a nice color. I'll take the gray one." She's like, "That's not gray." Like, "What color is it?" She's like, "That's green." I'm like, that's not even close. They're not even close to each other. So for all I know, this is like the brightest shade of green in the history of green. I would not be able to tell. Yeah, the grays give me trouble. One time I bought gray pants. Now this one I don't think is fully on me. I bought gray pants. They were comfortable. I liked them, and I went to work under the fluorescent lights, and boy, it was the brightest shade of purple you'd ever see in your life. And I looked down and I actually saw the purple, but it was under different lighting. So that one might be on my environment, but still, it was like really bad. So that overlap is what we're interested in here. So again, you can take it, slide it on up, and you could see that there's a difference in color. The overlap produces a different color. All right. So I'll leave them separate. When you put it all together, really the only area I'm interested in is the part that's in this little, well, it's not an ellipse, but like sideways Stewie's head from Family Guy. Ovalish. So this would be only this part is A and B. All right. We call this the intersection. Which, if you think about it in terms of everyday life, yeah, that feels about right. Two roads intersect. It's the box. Don't block the box. That box is the intersection. It's not as simple as they make it seem in an algebra class. Like find the intersection of these two lines. It's so abstract you don't really think about it as being overly meaningful. But when you intersect areas, it becomes a little bit more obvious. You could actually walk down a road and stand at the intersection. And it could be a variety of different places as long as you're in the box. Now, same sets, A and B, but this time we want what's called the union. All right. Now, sometimes in math, a term will define itself. Intersection, I think, is one of those, where they're in common, where they have the same area, where they have the same value sometimes. All right. But the union, maybe not quite so much, but you'll see after I explain it. So this symbol is set notation for OR. My handwriting just took a walk on me. It's a nightmare in the best of times. And actually, it's the reason why I have to use this app, because it smooths out my terrible handwriting. If you saw it on paper, you'd wince. All right, set notation for OR. Treat it the same way you would treat the V. All right. So in terms of the logic of it, that's the case of I'm wearing shoes or socks. Like if I'm wearing shoes and socks concurrently, that works, that satisfies it. All right. So what I'm looking for is the total coverage of the two sets. I'll just say of the sets. All right. All right, so total coverage of the two sets, but I could still use my little animation here. I mean, it's not a professional animation, but and you can find those online. You can find GIFs and other animations that show this stuff. Uh, but yeah, it's just the idea that you're taking two sets and combining them together, and looking for any part that's covered by really any shading whatsoever. All right. So if I go in closer here, and again, we're going to get the same result in terms of what it looks like. But now I only care, well, not only, but I care about the parts that are shaded in any way. Maybe it's single shaded, maybe it's double shaded. The only parts that I'm unconcerned with would be the parts that are completely white, no shading whatsoever. All right. So with that in mind, I have, again, set A and set B. I could use whatever color I want. And in fact, I mean, I'm using color because I have the ability to do it. I'm not going to ask you to whip out the highlighters every time you draw a diagram. But, you know, like at least if you see it at least one time up here, you can kind of get an idea. But I'll use green, I guess. But I would shade, this would be my final product, any part that was even touched by shading when I combine the two sets. All right, so that's the union. And you know, like if you use the concept of the union in, you know, like everyday terms, I guess you could say like a union in the workplace. Yeah, so I'm a math teacher. Somebody else is a computer science teacher. And I also teach computer science, so I'm both. And then there's people who only teach the math, only teach the computer science, you know. So there is some overlap. You know, so in our union of two departments in a school, there would be some overlap. I would still count that. If I'm really taking the union of my two sets, I'm going to look at it and say, all right, anybody who's math, anybody's computer science, anybody who's math and computer science, let's all get together. That's going to be our union. All right. The other analogy I use is marriage. You know, except in the circumstances, what, you know, like the old case, what's mine is mine and what's yours is mine. You know, not that. But like if you yeah, I'll just say get married. I don't know what the right terms are anymore, but like a partnership, you know, you combine forces, I guess. You know, you're gonna have some money before you get married, so, and the other person will have some money before you get married, but then you'd have some overlap. All the stuff you bought while you're married. You know, so that all of that would collectively make up the union. All right. So the only difference is, compared to the intersection, you're interested in the collective rather than just what you have in common. All right. So using my marriage analogy, this part here, or this graph here, would be only the stuff you bought together once you were married. All right. You bought a car together. All right. So that's both of yours. But going in, you had a big screen TV. The other person had, you know, an exercise bike. Like those are your individual properties. But then once you unify, anything that was anybody's belongs to everyone. Right? So that would be the case of the union. And really, honestly, I would say this is all stuff that you probably already intuitively know. It's just we're trying to get the notation, the verbiage for in the math context down. All right, so I'll say right now, in the beginning, it'll feel like I'm overcomplicating things for the sake of overcomplicating things, but I promise it's for a purpose. All right, and it will get easier if it's something that's not really jiving right now. The not symbol. We actually haven't talked about this yet. We talked about the if then, but we didn't talk about that little tilde. That's a not. All right, so that's not A. All right, and one thing that I didn't really talk about, aside from the not, is what about anything that's not A or B? You know, really everything else. All right, so if it's not A, it's not B, then what is it? Well, it would be everything else. The rest of the rectangle represents everything else. Let's just make a little note of that. Very little note. Everything else. All right. That's what the null space means, but still within the rectangle. All right. So anything aside from A or B. All right. So you think about, I mean, that could be substantial. If you're talking about, like, again, going back to my marriage analogy, you're talking about this shaded region representing the possessions of me and the other person, then everything else in that context would literally be anything that's not possessed by me and that other person, or the other person, which would mean like the rest of the planet. So my case is a very simple case, just two individuals. The opposite of that would be everybody else on the planet, or otherwise, right? So sometimes you could be really kind of honing in on a very small scenario, a very small set of information, but the opposite of that could be extreme. You know, when we get to probabilities, you'll see how that goes, because sometimes we want to find the opposite of the thing that they're asking us to find, because it'll be a simpler thing to do. All right. So in this case, I have sets A and B. Not that would be anything outside of the circle for A. All right. So I'll just go straight to the shading on that. Oh, I selected the wrong tool. This one's kind of a pain to shade, but I'll give it my best. Yeah, I always end up going outside the lines, and I feel my inner kindergartner just flipping out on me. So it's like that, but then you know what happens is the app is kind of funny. I can erase some of it, but then it erases too much, and when I want to trace over it, it looks terrible. So just kind of do the best. And again, you're probably not like I said, you're not using a highlighter. You just do a little, lines like that. I should probably use a darker pen, like this. Just kind of work your way around. That's fine too. And that's probably the way most people will go about it. But this is the set of everything except for A, right? And when you look at it in that context, not A, well, what's A? I am wearing shoes. The opposite of that, I am not wearing shoes, right? So it's pretty straightforward when it comes to things like that. But generally, what we're looking at least when we get into probability, is the event that occurs and the opposite of the event that occurs. Right? So we might find the probability that it's going to rain tomorrow. We could find that online. All right? We could also find the probability that it's not going to rain tomorrow. If we know one, we could figure out the other. All right? So we look at it in an individual sense, but then we could draw other conclusions based off of that individual outcome. All right? So that's I know it's notation heavy, but it's going to set us up nicely for the next part of the unit. All right? Between this, Venn diagrams, talking a little bit about logical reasoning, and then getting into probability. All right? But I want to buy you some time to digest this, and then also getting a calculator and things like that. All right?